structure, then it will, the kinetic energy from the wind, it will be transferred as a pressure to the structure. Wind forces of any structure therefore result from differential pressure caused by the obstruction of free flow of wind. So whenever we obstruct the free flow of wind, then there will be differential pressure. Because of that differential pressure, wind forces are coming. All right. So next, if we see, these forces are functions of the wind velocity, orientation, and which direction it comes, and area and shape of the structural elements. If the shape of the structural elements are tubular or I-beam, or here you can see beams, sides of building, cylindrical section, overall project area, for different size, shape of the structural element, there is something called a shape coefficient. So this also depends, like these force, wind forces is a function of wind velocity. Here you can see the velocity and area and shape coefficient. So wind force is a function of velocity, area, shape coefficient. So shape coefficient depends on the shape of the structural elements. Okay. So now let us see wind forces on a structure or dynamic problem. Okay. Here you can see wind forces on a structural dynamic problem, but for design purposes, it is sufficient to consider this as a equivalent static pressure. So design purpose, we can consider that as a equivalent static pressure. For an ideal fluid by Bernoulli theorem, rho v squared by 2 plus p naught rho naught, right? Rho v squared by 2 plus p. So here this rho v squared by 2 is the q0. Q0 is nothing but the dynamic pressure. Okay, so rho v squared by 2, that's the term where the velocity comes. Here if you see force equal to 0.0026 v squared CSA, right? So this v squared depends on the velocity of the it's actually the wind velocity. So forces depends on the wind velocity, that comes from the Bernoulli's theorem. So rho is the mass density of the air. You know, air has mass, so mass of m v squared, right? That's the kinetic energy. Kinetic energy also we know half m v squared. So it's a mass coefficient and velocity term. That's it's there. And p naught is a static pressure. Okay, so rho v squared by 2 plus v, that is a static pressure and velocity at any point on the object. That's the velocity of the approaching free flow. V naught is the velocity of approaching free flow. The term v squared, rho v squared, designates the dynamic pressure. Thus, the sum of the dynamic pressure and static pressure is constant at all points. It is convenient to resolve the wind forces into horizontal and vertical components. So we can conveniently resolve the force horizontal vertical. So there is some horizontal force is FD, drag force. FD is the drag force, and FL, that is the lift force. So lift force depends on the coefficient CL, that's the lift coefficient, and CD is the drag coefficient. A is the area, exposed area, Q is the pressure. So pressure times area into coefficient, that becomes the wind force, horizontal wind force and the vertical wind force, that we can resolve the components, right? The magnitude of CD and CL depends on the shape of the object, it is and its orientation in the wind stream. In wind stream, how it is oriented, based on that, this CD and CL, it will vary. So this wind pressure into area, and then this coefficient, drag coefficient and lift coefficient, it depends on all these forces, all these factors. So let's now see the API wind force formula. American Petroleum Institute recommends the following formula to calculate the wind force on offshore structures. So wind force, just now we have seen, this is the projected area of the object, shape coefficient, and then beams 1.5, side of building cylindrical section is 0.5. So here we need to see this cylindrical section. cylindrical section, because mostly we are using in a jacket structures and all cylindrical only. That's why it's a 0.5 is the shape coefficient. Overall platform project area, whenever we do the top side calculations, that time it becomes overall project area, we will be considering it. So overall project area is the overall project area is 1.0. And there is one more factor, height factor. Height factor, so velocity equals to V10, and there is one more factor, y by 10 whole power x. So v is the velocity and v naught is the velocity at 10 meter above water surface. So we need to see this 10 meter above water surface. Y is the height above water surface in meters. So this is the water surface, means y is the height above water surface. So this is the velocity. So velocity will get increasing when the height increases. That's a y by 10 power x. X is the exponent, usually assumed to be between 1/13 and 1/7, depending on the sea state, relative distance from land, duration, and the wind velocity also, design wind velocity also. Okay. So this is the factors we need to consider. There is one factor is a height factor is there. So when we go to this, here you can see the height factor. See, this is the y by 10 in y in meters, 5 meters, 6 meters, 1 meter, like that. And y by 10 whole power x becomes like 1.1, 1.3. So here in this velocity depends, like velocity at 10 meter into y by 10 power x means like that factor can be 1.10, 1.20, 1.30. It depends on this 1 by 13 that we have seen, right? That is for gusts, and 1 by 8 is for sustained wind. Sustained wind and gust, there is a difference between these two. So wind has a static as well as dynamic component. The dynamic component is the gust one that we will see it y means a factor. And ABS wind force also, if we see it, F equal to 0.0623 Vk square. Vk square is a wind velocity, CH and CS. So CH, CS and all it's a factors, like CH is the height coefficient, another CS is the shape coefficient, A is the projected area. So here we can see, we can say some factor wind force is nothing but 0.0623, and then Vk square, that's I think 10 meter velocity it will come. And then there is two factors, CH and CS and area. CH is the height factor, C is the shape coefficient, that we can see cylindrical shapes is 0.5, hull 1, deck house 1.0, isolated structural shapes 1.5, undecked areas rigged 1.25. So these are the shape coefficient and height coefficient. The following height coefficients are different specified by ABS. The height is the distance above water surface. 0 to 10 feet it's 1, and 50 to 100 feet 1.1, 100 to 150 1.2. Every 50 feet so 0.1 factors increasing. After that it's 1.37 and 1.43. These are the factors we need to consider. This is as per ABS wind force formula. And then we can see about the DNV wind force formula also. Here we can see the DNV wind force. Here it says DNV wind force is rho by 2. That's a mass density. Velocity Vyt is the wind velocity averaged over time interval t at a height y meters above mean level. Mean water. C is the shape coefficient. A is the projected area of the member normal to the wind. Angle between the wind direction and the axis of the member. So that means this is the, suppose if we have the shape like this, and this is the wind direction, means projected area will be, this is the projected area, that means this portion it will come right with height wise. Okay, suppose if the angle is here 0, right, like angle between the wind direction and the axis of the member. Axis of the member is this one, wind is like this. Suppose if we have somewhat same shape but the direction is like this, means the projected area will be different, so we need to consider this angle. In DNV formula, v weight is a function of time, height, gust factor. So gust factor also important. We need to understand what is gust factor. So in DNV it becomes like a gust factor also is there. Function of time, height, as well as height factor is velocity is function of height, and gust factor also it is a function as well. So here we can see alpha dash is the gust factor. Gust factor 1 for 1 hour interval, and beta is the exponent for height factor. Beta is the exponent for height factor. Alpha is the gust factor. 1 hour interval means 1.0, 1 minute means 1.18, 3-second gust means 1.33. So 3-second gust alpha is 1.33. The gust factor is more. So suppose if the interval it comes down, then the factor gust factor is increasing. So 3-second gust factor is more compared to 1 hour or 1 minute. Okay. And y is the height above the mean water level. Average wind speed over 1 hour interval at a height of 10 meters above the water level. So this is like API also. And then here we can see DNV height factor, 3-second gust, 1 minute interval, 1 hour interval. So we can see like 3-second gust, and if it is 1 hour interval, y by 10 whole power beta, that factor is varying. And shape coefficient for structural numbers of finite length is defined as C equal to Kc dash. K is reduction factor, C is the shape coefficient of members of infinite length. K and C dash are provided in the appendix B in DNV. One must be able to refer proper coefficient. Okay. Solidification effect of plane truss or a series of columns is taken into account by using solidity ratio and the effective shape coefficient. Okay. So what does it mean? It means when we have one member and immediately nearby another member is placed, when the wind is blowing in this direction, it will obstruct the wind. Wind effect, whatever the force is coming here, this member it will be observing most of the wind force, and when it comes to here this member, it will not have the same effect because it's immediately in close vicinity to this member. And this is something called the effect of solidity. Solidification effect, they used to call solidification effect. So this we need to take into account by using solidity ratio. That's already taken care here by using this factor 5, and say effective coefficient of each members. We can see CE and phi are also provided in the DNV rules. Shield effect, members located behind each other is taken, the shielding effect is the eta wind force. Shielding factors, this is actually shielding. Shielding means not solidification, it's a shielding. Shielding means immediately that member is in the vicinity is there. So this is the shielding effect, not the solidification effect. Huh? So that we need to see the difference is there. Okay. Solidity ratio is different than the shielding. Shielding is the immediate vicinity. I think I mistakenly told this one. So shield effect for members located behind each other. For members located behind taken into account by multiplying the shielding factor. Shielding factor is different. Okay. Unsteady wind forces. This is for the vortex setting. It would come. We need to consider the unsteady wind forces, vortex setting. So here, slender or relatively flexible offshore structures such as derrick flare booms may be subjected to wind-induced oscillation of large amplitude and severe stress when damping is small. So what does it mean? Like if when the structure is very slender, some flare boom kind of structure and all very slender, that will be subject to wind-induced oscillation and large amplitude. And this is especially true when the structure or structural component is free to oscillate in a bending or torsional mode simultaneously. If it's bending or torsional mode simultaneously, it can free to oscillate. This type of motion become quite violent and reach catastrophic amplitude in few cycles of oscillation. So it can oscillate and then it can collapse. When cylindrical objects are loaded with the high wind speed associated with the high Reynolds number, vortex formation may be caused periodic alternating forces perpendicular to the wind direction. So what does it mean? It means we have the one tubular member, okay, cylindrical object are loaded with high wind speed. Wind speed is very high, okay, associated with high Reynolds number. Reynolds number also very high, and vortex formation. Vortex formation means behind this one. Vortex formation may cause periodic alternating forces perpendicular to this is the wind direction. So perpendicular to wind direction means this is the one. So it can oscillate like this, right, perpendicular to the wind direction, resulting in a vibration structure. The vortex frequency of vortex setting is frequency. It will start alternating forces, right? It may cause periodic alternating forces perpendicular to the direction of the wind, resulting in a vibration of the structure. So the frequency of this vortex setting is given by SN. SN, it's a Strouhal number, and velocity divided by ratio. So velocity divided by diameter into SN. That's the frequency. What's the frequency? Vortex setting frequency. So average value of Strouhal number for circular members 0.2 when Reynolds number is less than 6 times 10 power 5. If it is more than 6 times, SN is 0.4. It's almost double, 0.2 to 0.4. For a circular member, vortex setting is strongly dependent on the Reynolds number of the flow. So someone can question you like for circular member, vortex setting frequency or a Strouhal number. Strouhal number for circular member vortex setting frequency is strongly dependent on the Reynolds number of the flow. Okay, it's strongly dependent on the Reynolds number of the flow. Strongly dependent on the Reynolds number of the flow. In general, when less than 6 or Reynolds number is less than 6 times 10 power 5, the setting is random. So setting is random. Reduced velocity factor is defined as, so if it is less Reynolds number, that vortex is random, and then reduced velocity factor f. This is nothing but velocity reduced velocity factor. Huh? So velocity divided by natural frequency times diameter. So this is how we will calculate the reduced velocity factor. This is how we will calculate the reduced velocity factor. So f dash is the fundamental frequency of the member vibrating in line with the flow. So this is the fundamental natural frequency of the member vibrating in line with the flow. DNV recommends the following regions of resonant vortex setting should be considered. So DNV, it says that recommends following regions of resonant vortex setting. One, if when reduced velocity factor is there, right? FF. If it is less than 1.7 and less than 3.2, that means inline excitation may occur. If it is between 4 point, if the reduced velocity factor, if it is between 4.7 to 8, then cross flow vibration may occur. then cross flow vibration may occur. So next one is, if you see the figure 2.3 shows plot vortex shedding of various vibes. It is noted that F is the, here you see F, F is double when the Reynolds number is greater than 6 times 10 power 5. Yeah, if it is less than 10 power 5, this is F, this is the, this factor is, what is this factor? This is nothing but the reduced, I mean the vortex shedding frequency, right? F is SN times V divided by diameter, right? So SN also varies, 0.2 or 0.4. 0.2 means Reynolds number less, 0.2 Reynolds number more than 600, it's 0.4. That's why it's a double the times it comes. This is nothing but the frequency, shedding frequency, vortex shedding frequency, frequency of vortex shedding, frequency of vortex shedding. So we can see vortex shedding. So forces can be calculated. How we can calculate the force? F 0.5 times mass into fluctuating force coefficient. There is something called force coefficient also there. Force coefficient and area into velocity squared. Area into velocity squared, okay. Then this force coefficient is the fluctuating force coefficient. Okay. Fluctuating force coefficient. So this CF is provided reference by DNV. If greater than Reynolds number is greater than 3 times 10 power 5, so force coefficient C equal to 0.2 and dynamic load factor 0.5 by eta, that is damping. Dynamic factor, load factor is recommended when resonant wave setting is likely to occur. A damping ratio of 0.005 is recommended. Okay. So here we can see for this velocity and for this diameter, we can see what is the vortex shedding frequency. This we can calculate. Okay. So let us see some examples. So here 36 inch diameter pipe, height is 40 feet above an offshore platform deck, which is 10 feet. 10 meter means 30 feet above water surface. Maximum wind speed is 150 miles per hour. Calculate the wind force. So first we need to see the Y value. Y value 30 plus, always it's 30 is 10 meter, right, plus 40 by 2, because at the center we need to calculate the force. This is a 40 meter height, right, flare. So this is 40 feet height, and from water level it is, water level is 30 feet. So this is the value 30 plus 40 divided by 2, this half we need to consider, right? So that's okay. Y by 10 is 1.52, V equal to 150 into 1.06. Here you can see APA formula, right? V squared CSCA, right? So here what is the factor it is coming? Velocity we are converting into kilometer per hour, 0.0256. 1592 is the velocity miles per hour. 0.5 into 3 into 40. That value is here, it's coming 3 into 40, and all. You can see the area and all, it's coming, right? V squared into CS into A. CS we need to see 0.5. Because it's a cylinder pipe, right? So 0.5, 3 into 40. So here we can see 417.3 kilonewton. AB is also, it has its own formula, and DNV also it has its own formula. We can calculate it. Next one is the same flare pipe. Okay. Point inch wall thickness. What is the critical wind speed? They're asking critical wind speed. So natural frequency we have to calculate. Natural frequency we can calculate C by L squared into square root of GEI by W. It's a formula, natural frequency formula. C is the 0.56 for fundamental mode. G, E, I, W. I we can calculate from the diameter and thickness. L is the 40 feet they told, right? So from that we can calculate. So this is the term, and F dash we can see natural. I mean this natural frequency, fundamental frequency is 6.17 cycles per second. That's the fundamental frequency. And from figure 2.3, when the wind speed is about 60 miles per hour, frequency of what setting is. So here we can see velocity we know, and f dash that's not going to change. F dash we know 6.17, and diameter also we know 36 inch. Right, that's the velocity reduced factor. Right, and f dash is the natural frequency. So if this is the one, we can calculate this f of value. F of value we can see, for example, wind velocity of 160 miles per hour. If this is 60 divided by 6.17 into 36 inch, right? In that, then f of value becomes vortex setting 6, f of greater than 4.7. So from here we can calculate this f value. F becomes 6. Wind velocity is 60, 36 inch. Then this Reynolds number is